40 more boots.
God.
Your bladder may actually explode.
That's the last thing I'm worried
I will give you a Bud Light. You should be fine.
So, I want to believe that everyone is ready to complete. Okay, I'm just checking if the green bar is popping up. It's not that I'm uploading to myself. That you have enough information to start preparation of the presentations. Yesterday you did a heroic feat. You stayed for 2 labs instead of 1 in 1 day, in fact. And we covered mostly everything that we need for the teaching in chess how to use Flask and to jump into actual research. Many research projects that will be main component of the course. There are a couple of things that were not covered yesterday and that will not be covered because of my travel plans, unless flights will be cancelled and I will demonstrate sport personality. So this is recordings of the first part with this cations anions spin polarization. Momentum dispersion is not here. Sorry, but heating and molecular dynamics, yes, movies and naturalistic bands are not there. But in addition to things that are declared here and not covered, there are a couple of things that would be great eventually to cover. I may cover it after when you already start research, but just to give you a heads up and encompass your QA question. Right now, you do know how to compute spectra when the model is in a singlet state, when you do not have spin alpha, spin beta. But if you describe metal organic complexes, they are often like quadruplets or whatever, and you need to monitor their absorption spectra. So there is a unit of protocol that allows to get spectra for spin polarized. This would be really good. Orbitals. If there are spin polarized populations, there are orbitals for alpha and beta. They often do not coincide in their shapes. And it helps your intuitive analysis. We will not cover in the course, but in fact, it is possible to do also momentum resolved spectra, momentum resolved. Something else. Just to mention. For your practical research after the course, many of you could be interested in normal modes analysis in Flask. This is also just template info, and as soon as you have normal modes, you may want to develop density of normal modes or absorption spectrum in infrared. We are not. I'm just declaring what we are not doing. There is no time before the presentations, but it is also one of the possible focuses. When you do have molecular dynamics, you may want to show trajectory of temperature, just to judge how far it deviates from average temperature. It doesn't fluctuate, it fluctuates less. It's a good model, but if you do like H2 model, H2 is just oscillate. So it's a transition from oscillations to statistical description. In addition, you know at each time step you have electronic structure, set of orbitals. If you apply correct two molecular dynamics, you can see how electronic orbitals jingle during molecular dynamics. And many other things. Whew. Posting spin polarized dose. It's important for everyone. If well, I will try to be extremely convincing. I talked to him before, but if he will resist, someone of us needs to cover it because all materials change. And if Christian has a lot of steam, you can try to learn on your own about spin polarized orbitals. No, I will not talk about it right now. You will talk. Oh, yes. you may say.
Yeah.
So two theorems, a way to describe external potential, correlation, world where electrons do not interact with each other, and in such world, the only part of the Hamiltonian that we can treat with analytical function is potential, and kinetic energy is still described, will be described in terms of solving Schrödinger equation. And this equation is important. When we will be doing this, you will return to it. So if you have photographic memory, memorize it. It will help. So total energy is whatever it is. Kinetic energy is something that we can find old-fashioned based on wave function, and their difference response to variation of the density is potential that is used in the equation for one electron orbitals or independent electrons. Okay. And then, since electrons do not interact, we practice separation of variables. So instead of wave function with many variables, we are going one equation and one wave function with many variables. Many variables with one independent variable. Many equations with one independent variable. Equations here. And because electrons do not interact, each Schrödinger equation with each little fraction of Hamiltonian will be the same. So instead of solving like 100 equations for 100 electrons, we solve one and assume that solutions will repeat. We just populate them according to Aufbau. Yes? What are the other Pauli principles? Aufbau means build up. Right? And we did a derivation. You all have derived proof that if you do have wave function of many electrons, suppose a state of determinant state of the one electron quantum orbitals, which are only occupied quantum orbitals, occupied according to Aufbau and Pauli, one can use this wave function to construct first multi-electron densities and then project it only on one, on three Cartesian dimension, make one electron projection of a density. And it is the only thing that we need to make density function theory to work. This is a beauty. So you have a feedback connection from multi-electron object back to one electron. Well, it is many electrons, but it is parameterized by one Cartesian coordinate. So density of all electrons at one point of space, right? So it's very, very intuitive. Same as it would be like large collection of point charges in classical mechanics, classical electrostatics. And then you practiced orthogonality quicker than I did. And here is was your answer, right? So each first, second, and if more, each orbital squared, or absolute value squared added together of the same variable will give the density of all electrons, but as function of one variable. Okay? You will need this equation as well for the quiz. Since you have derived it, you will be able to write it down. And I do have it in the simplified shortened form. Yes, this one will be sufficient. So here it is how we are getting the potential that depends on only on three Cartesian projection. Here is how we get density when we do have orbitals. And we need to make a self-consistent cycle, closed loop that allows to run it and through iterations arrive closer to answer. So again, looking back onto Hartree-Fock, there is no chance to solve multi-electron problem in a format of diagonalization of matrices, because it is a correct way, but the matrices are too huge for us humans and for them computers. And there is a way to project linear problem with many degrees of freedom or big dimensionality, or non-linear problem with much smaller number of degrees of freedom or dimensionality. But non-linear problems are often solved in self-consistent style. If you are in physics background, this word should be near and dear to your hearts. Okay. What is functional? What is functional in the context of density function? The rightmost, frontmost is the spot for person who answer questions.
Like a function of a function, basically.
Yes, and in more narrow sense, of which function? What is our argument?
The
Function of
density.
which function?
Density.
Yes, density. And what we are getting in return?
Energy.
Yes. So we are targeting total energy as function of density. Good. I was intending to write it down. Otherwise, there will be no pedagogical value. Okay, okay, let me check myself and try if I am able to remember anything of what I'm showing to you guys in slides. So what do I do if I am a computer who solves DVT? I want to ask a question to Russ. Remember a week and 1 day ago, we were plotting orbitals, right? And if you take healthy, correct wave curve and generate orbitals out of good wave curve, you get some shapes that you can analyze. But if you randomly take a no wave curve, or what do you get? Just describe by words what do you get?
Random densities.
Random densities. Okay. So since we are going through self-iteration cycle, the density is like feed in, fed out, and goes through cycle. On the first cycle, it is random. So you can just some noise, which obeys normalization condition. So random number, density spread over the whole simulation cell. But if you apply the right procedure, it will excuse me, consolidate it around ions and do good thing. So how do we go? What do we need to start with random density, which we will update later. We do need to compute potential. Later on, we need to solve this little h times theta, which is dr square minus h r squared v, and here the potential does depend on position in space, but it is also a function of nav of density. And the whole thing, well, I use a different title for it. acts on unknown function of theta and generates epsilon I theta. So we do need to solve equation for quantum orbitals, right? I'm skipping a little spot here, which I will complete later. There will be some connection. So this density would allow to formulate potential somewhere. But as soon as we solve these quantum equations, so we are jumping to the auxiliary space, auxiliary world where electrons do not interact with each other, solve this one electron equations, but then use them towards our favorite equation that you guys have derived. Theta I absolute squared from 1 to homo, highest multiplied equals rho of pi. And then you use computed density as a feedback. It's not seen there. Density. And then from this density, somehow you develop this potential, right? So you need potential as function now of density. In fact, you go directly in the codes. So there, since you know Taylor expansion, it's your favorite subject in calculus. It's a reason. It's a first practical reason why one needs to learn derivatives, because Taylor expansion allows to reproduce any function based on a couple of values to interpolate, right? So there are interpolation formulas based on Taylor expansion. Similarly, there are analogous interpolation formulas in the functional calculus. Functional, not like it's cool, but functional for functionals instead of functions. So the way how the density is connected to this potential, so V as functional of density, one can, well, I'm not telling for the record, although we are recording, but it is like coefficients, some integrals of density in 1 power plus another coefficient and maybe gradient or derivative of density, and then in another power integral. And then here there is no derivative, here is the first derivative, you can go to the second derivative. So it's by the ideology, by the basic principle, the way how the potential is reconstructed out of density is analogous to Taylor expansion. You cannot tell it is Taylor expansion, it will be wrong. But the basic idea is the same. So in Taylor expansion, you do have like f of x equals f of x 0, 0. This origin is not very good. Plus f prime of x 0 times delta x, right? Here, no derivative, there is first derivative. No derivative, there is derivative. Okay? Do not reproduce it in public, but keep it in mind for having a straight logic how things are organized. So it is, there are analytical expressions. We covered very oversimplified Thomas Fermi equation. We can cover actual local density approximation equations if I will have connection on coming Tuesday. But as soon as you go further than the first term, these equations are published, but they like each equation is 1 page long. And if you decide to select it as your profession, you cannot do anything else. It will kill all your time. But there are maybe a dozen people in the world who enjoy deriving new functionals and naming them after their names. Okay, and if you want to just give feedback to original way, to the logic how it was derived, you can tell that in fact the potential is functional derivative of total energy minus kinetic. So the potential is in fact written down as expansion equation. But if you approach it not practically but philosophically, the total energy must be a functional of the density, and total energy must have analytical equation. Or total energy minus kinetic energy is the energy rather than the function derivative is fitted into ideal but unknown perfect function, which is promised to us by theorems. Okay? So our goal is to reproduce this feedback in the flowchart. I will mumble a few comments more, but you basically know what to do. Right? So we need to remember our favorite character of this class, a programmer in the bathtub. So we need to decide when to stop this cycle. So before we start this, yes?
I just have a question. It's probably dumb. Do the units work out on the thing you bought?
Yeah, I was wondering about that too, actually.
We have energy minus energy over density is equal to energy.
What is the unit of energy? Whatever, electron volts, or what is the unit of potential?
Normalized energy.
Yes, it is. Units of potential are chosen in such way that I will write in this space that if you integrate potential times density, you will get energy. Okay? Programmer in a bathtub. How do we stop? So at the beginning, we need to set up tolerance. Sure. This touch screen doesn't allow me to touch. Doesn't copyright. This calligraphy means E sub TOL, if you're taking notes. And the cycle, when we compute the energy, we should compare total energy found at the previous step with total energy found at the current step. If they coincide, it means you won the lottery ticket. You found the absolutely correct answer, which rarely happens. But if this difference is less than your desired tolerance limit, it means that you are sufficiently good to publish or to whatever to stop the cycle. And when you were in the practical aspects, when you look for the content of the file OSICAR and you update its content each second on a screen, you see how it develops. So it goes through electronic iteration cycle. And one of the columns includes the difference between previous and next energies. And as soon as this difference goes less than whatever you request, it stops. And either goes to computation of observables if you have 0 ionic iterations, or it goes to ionic iterations itself. Make sense? So you do watch it. Okay. I wasn't too wrong trying to practice my model. Lot of energy, potential, one electron stuff, and density, and then feedback. Okay? And we are going just to feed it into flowchart. Why? No reason. Codes are already written and they're working. But if we will be moved to inhabited island that has no programmers but has a lot of computers, and you really need to implement density functional theory, you will know how to program. Which is not a very realistic scenario, but who knows. Same, but with the code. And also, I think that it will be big torture for you to request memorizing the equations. You probably came here for practical implementations and the research complement to experimental things and practical research rather than diving deep into theoretical aspects. Therefore, there will be. So, if I need to go to exam and I don't remember equations, I take with me a little cheat sheet. And if I want to do it secretly so that no one observes it, and this cheat sheet is very small, is there a specific colloquial word? No? Just small cheat sheet? Okay. I'll first declare what we will have, and then distribute. So each of you will get stuff like this. Some equations. So you can either pass them around or, after you get the quiz to complete, or you can just pass around and tear off one equation of each sort. So you recognize this Schrödinger equation, this your favorite equation of the total density. Here is your comparison with tolerance limit, and here is the answer of total energy. But, well, we are not in kindergarten, but we need to place stickers in a right order. So prepare. I will announce it in a short time. Once again, we are not writing codes, but maybe once you will hire a professional code writer who will write codes for you, or maybe you like doing it yourself. But there are many programming languages. There are different syntaxes. But if you want to communicate basic idea between programmer and a person who needs a program, or between programmers of different work in a team, one can simplify basic idea in the flowchart language. Right? So instead of, because same operation can be expressed on different syntaxes in different programming languages, one often uses for input and output, it makes something like round or oval, or direction data transfer arrow, for mathematical operation rectangular, and for forking, branching, conditions, you just do triangle, right? So there is a task. Formulate a Kohn-Sham algorithm as a flowchart. So if you think we can reproduce equations without stickers, which will be especially generous with credit. But don't worry if it exerts a challenge. There will be quiz action. You can do it. It's fun.
I'll do my best.
Take one and pass around. It's not each piece of paper is not a complete set. It's only one of equations, but as you pass around, you'll get everything you need.
No. Sure. Yeah, you just put it in the box. Then I'll shoot for it.
Landed. Oh, jeez. Let's just go like clockwise. Yeah. Oh, I just kind of start passing it. Landed.
Wait, I already have this one.
Yeah, because we said clockwise halfway through of our mess. Oh. This one's different. Again. Here you go. I'm just pulling them off and then doing it after I get them off. Well, yeah, I mean, so am I. Landon's like actually trying to put them on as he's getting them. This one already. I think I have that one too.
Everyone got enough stickers? It should be like 6.
I need one more.
Oh, okay, I have 6. I got 6.
Or wait, 6?
Yeah. There are 7 boxes. There is a joke about the police officer who was not liked by colleagues, and he was like more manager than rather than real investigator, and colleagues decided to joke on him, and when he was it was needed to check his personal weapon, you know, you need to clean it, disassemble, assemble, they throw in one extra detail. The person got crazy.
So which one is missing?
Just one of the little boxes, I guess.
I think the output's probably missing.
No, the output's definitely.
But 6, I think this is the input, they're just like, you give it parameters.
You got 6?
It's right image. Times.
Which one do I skip?
The extra box is messing with my head.
Because you definitely have to have a thing that you like come back to potentially, and you definitely have to have like a condition. Right? So I would just skip that one. Skip that.
1, 2, 3, 4, 5, 6, 7. Okay, so everyone who is registered for the class is 6, so everyone will have a chance to come in front and share. Yes, and practice sticking one sticker. Christian? Whoever comes first has more luxury because you have or more challenging. The last one will have only less to guess. Okay. Yes. Oh, I need to collect things before doing it. Yeah, so please complete and I will collect and then we'll do it together.
No? You look flustered.
Yeah.
Okay. Great. But arrows are missing. Keep doing.
What?
Landon's flustered.
I have the order. I just don't know where to put them. Or like, you want me to put these? Or
I think it's just skipping
Put arrows.
these
to have it complete.
here.
Oh,
Skip this one.
Oh, it's
Oh.
that what?
Which box is skipped?
Russell should know which box to skip because he practically generated the content of this box. So random density,
Okay.
arrows, how to loop.
the treasure sure is that, but I don't have a sticker.
Enough.
Yeah, I mean, I don't have a sticker there, that's why it's,
screwed up some.
Yeah, apparently.
yeah, I did too, actually. I put mine in.
And I had more faith in you people.
Well, I mean, I don't know. That makes more sense to use that box because, like, you can just skip over one of the first.
Well,
ones.
right,
Like,
yeah, that's what I was thinking. Plus
Okay.
straight harder.
3 more.
Yeah, I skipped the wrong box.
That's okay.
Why does it come down to that?
What's time? I was not stop watching you and doing this on time. I'm just curious.
It's 11:45. Yeah.
Okay, so you're not over time.
Obviously.
Okay.
Plus or minus not much though.
Probably 30 seconds.
Yeah.
So this one. This was random. I hope camera is not focusing on me while I'm doing this. Who was it?
What now?
One more for the orbital, right? It can be paired up and down.
And for to put this one.
So I'm curious how
It's
it's more
Okay. The start is nice.
Great finish, man. That's great.
So you find density, then you shouldn't do fish right here.
The whole
Yeah,
word.
finish that too.
It's not good.
Right.
So before we go through this,
It's not.
before we try to fill it together, let's see that it was Russell.
Oh, you're kind of making me worried that it was.
Yeah.
I don't want to do this.
Just let's look on the options and then we will go and do everything in a right way. Maybe something is correct. So one, so I'm not showing names, so I'm not offending anyone. So what I like? You start with positions of ions, you end with total energy. Yep. And the other things are not too bad. You start with position of ions, you end with density, you have the forking condition. Before, so we skip it, but we compute total energy, of course, at each step. And it is right. So here everyone puts one guesses the initial density, then one goes into the cycles of all this stuff. So yes, density should be here, it's correct, but we do not have orbitals at initial time step, therefore it is random. But then the logic, yes, well, this equation would be better here. Typically, in the diamond box, we have a condition comparison with tolerance limit, and this is more like mathematical operation. This should be somewhere in here. The initial conditions should be at initial. This should be here. This is answer total energy. That's just to do that. Here, start with position of ions and selecting towards me. End with total energy. That's good. Well, you guess with random density, and this stuff should be like here when we already go to next step. But logic in a string, it's okay. I would put this one, density, the potential as function of functional density in here, and then continue, because the potential allows to find orbitals, and orbitals allow to find the density. No, density is guessed here. Here you start with when you do practical calculations, you start with positions of ions. R sub I is initial position, initial. You end with total energy. This is correct. The diamond box is on the right place, and it is good that Schrödinger equation goes after the potential has been defined. So there is some value. Start with position, end with total energy. Good. Define potential. Good. Use potential for orbitals. Good. Orbitals are used to find density. Good. And only errors are missing. And here, random density. Here. Well, random density, and this one would be better at this step. After you find orbitals, they are used to define the density. Now let's, I know it looks like silly because you have already completed it, but let's do it together. Christian already did his share. Daniel, would you like to help?
Yeah.
it was a rhetorical question. You cannot say no.
No, mine was the last one. Mine was the first one you looked at. One or two.
So take one of the 5 and put in a preferred position.
Yeah.
Right.
So should have been given one more.
Excellent. Many thanks. So,
Thank you.
Russell, will you please come?
I feel like the price is right.
It's not that I'm following how Russell is walking, but yeah, camera is. So select something and put somewhere here. We're focusing the camera on this. I don't know if this document projector will be recorded. Hopefully. Okay, so yes, excellent. But thank Russell. Right, good. Vijay would like to be the next. And I'll put my name here. I'll get your credit. Okay, Schrödinger equation. Yes, let's thank Vijay. Braden volunteered to put a sticker. Yes.
Don't screw up now, man.
Oh, I'll set up a trap. Fatima, would you like to put a sticker? And there will be challenging task for London.
Oh boy.
What is spin?
I was about to say that.
Did you guys argue about a question in the very first presentation last year? Was the possibility of quantum mechanics? Measuring
Excellent.
systems,
Well, thank you,
measuring
Fatima. London,
Yeah.
guess what you are going to do? Come in.
Fill in the box.
Connecting everything by
Oh,
arrows.
okay. Yes.
So it's random density and just draw.
There is.
And right, is it yes or no?
Oh, wait.
Or it better goes to not to this ugly box, but to the next one.
Yeah.
Because you pointed it at random.
Because now we have, we have a new interview.
Yes.
We want that.
Okay. Okay. And on the diamond, it is yes or no? No. Okay. And here it is yes. Excellent. Let's thank London. From now on, you are ready to write methodology sections for your papers. You need to type in these equations in Microsoft Equation Editor, give them numbers, first, second, third, and connect, instead of arrows, connect them by words. Okay? So we describe electronic structure with density function theory. Total density gives rise to potential that allows to solve Kohn-Sham equations for Kohn-Sham orbitals, which determine density, and the procedure is repeated in a self-consistent way until the tolerance limit is achieved. This procedure is implemented in software blah 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 with functional blah blah blah. And then go to results section. Or before results, you can tell the following observables have been computed: density of states, absorption spectra, and isosurfaces of orbitals. Well, maybe something else. Okay? So prepare. You will do methodology sections in your real life, and we will do reports of the mini research here in class. It's kind of suggestion what should be in this methodology section. It's not very long, it's maybe a paragraph, or if you do it with equations, it will expand to 2/3 of a page, but not because of text, but because of the spaces. You should be able to type in equations. If you prefer LaTeX, you saw that in the lecture notes that I shared, if you go from the view area to the side, there are LaTeX codes for each equation that I showed here. You can just, I guess, borrow and plug into your LaTeX document. Oh, some of you may think that it is the end of the meeting. Are you? No? Well, last year we were just writing it down, but you know what to do. And here, instead of stickers, things are placed here. So, we are not ending here. We are looking back to the old times when we were pretending that we are little computers. That we are little computers, and we remember one of the exercises when we were practicing optimization. We were algorithmically finding the minimum of the harmonic potential of a parabola. Step by step, by increments delta R, right? We were assuming that potential energy surface is provided, but we can find it only for such point where we are located right now. It's lift hands if you do not play computer games. It means everyone plays computer games. Okay. So if you play strategy games, you know the concept of fog of wars, right? So all area is hidden until you move there, and then it opens and you reveal the map. So same here. You can reveal only the area where you actually move to. So it's a review of the algorithm that we did at the end of the first chapter. So we do set up initial geometry, tolerance, limit, and step size. And then we compute the gradient of the potential energy surface, derivative over incremental position. Force. Multiply force, well, we also, mass should be numerator or denominator here.
Which one?
Here, there should be mass as well. Okay, I'll leave it for later discussion, especially for those who are in physics. There should be also mass to have it as an infinitesimal Newton solution. If this is a force, and here should be acceleration times delta t square over 2. Okay? So you multiply by parameter of time squared, and then you get increment of the position. So based on the curvature of the potential energy surface, you decide you go left, right, forward, backward, right? Especially if it is multidimensional. So then, and next step, you have new position values, old plus increment. And then you reveal from fog of war your next value of potential, right? At the step where we move to. And then we look if we're inspecting if the new value of potential minus old value of potential, absolute value, is smaller than tolerance limit. If yes, we have achieved optimization. If no, we are continuing for optimization problem. If you do molecular dynamics, procedure is the same. We just remove tolerance limit and do it infinitely or until number of steps. Remember, yesterday we were setting up like 10 steps of molecular dynamics. Otherwise, our patience will expire. So, gradient, time step, increment of position, new potential energy surface, and repeat. The program, yeah. Is there a connection between this flowchart and flowchart that you did derived on previous couple of slides? What is the connection? They both are flowchart. Yes. And anything else?
Your fog of war analogy.
Okay, fog of war analogy. Anything?
Output is energy.
Just repeat.
Output is energy.
Output is energy. Yes, this is correct. Output of energy. It is a trap. You need to think out of box. Everything you told is correct, but there is another connection. You need to literally think out of box. There are boxes. You need to think out of box. Try to. Daniel? Any connection between Kohn-Sham self-consistency cycle and geometry optimization self-consistency cycle?
One of the things is at the bottom with the energy, the difference of the energy.
Yes, it's a like way to stop calculation.
Yeah, it's the same structure. It's just you're looking at different particular values when you run it through.
Yeah, algorithmically, yes. But right now, we all are thinking inside the box. I really want you to make this guess.
So your question, what's the same or what's different?
What is a connection? Literal connection, not philosophical, not abstract. There is a literal connection.
Oh,
The
the
question-
output of that is the input of the.
Yes, yes.
Oh,
Let's applaud London. Yes, this is perfect. So, how do we know the potential energy surface. So Christian was very close, telling recovering fog of war. But how do we know this function U? If we are in force field, we have it tabulated. But if we are in density functional theory, we need to replace this part onto the whole algorithm that we did on the previous slide. So we define mu geometry, and for this geometry, we do find a total energy based on DFT procedure. Okay? So I'm merging this algorithm and the algorithm that you did derive. So in this black box, we need to squeeze in the whole page with other algorithm. Okay? We just need it bigger, and for for the sake of time, see, it's what you do. So at the step, you feed in the positions of ions, and then you go to electronic potential, orbitals, total density, total energy, repeat, 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 and then finally you get energy, and you compare this energy with previous one. Therefore, if you are looking, if you are scrolling, not scrolling, if you are updating the Aussie car file as you run job, you do see this electronic iteration cycles. But as they are done, you jump to next step, to ionic update cycles. And they kind of inserted inside each other. Right? So when we did, instead of optimization, we did molecular dynamics, you had 10 steps of electronic. It's a big cycle, but inside of each step, you had about like 5 steps of electronic iterations. So there are at least 2 cycles inside of each other. One for electronic degrees of freedom, another for ionic degrees of freedom. If you're taking notes, record it in some way. And I want to believe that this novelty was impressive enough that you memorize it anyway. Well, I like you. It is not out of the box, it is inside of the box. Whew. Now I want to believe that it is the last slide. I don't remember, but I have a feeling that 2 refining cycles agree, yes. What else? Chemical reactions, yes, it is the whole reason why we are staying here, right? So, again, sorry if you are tired of hearing it from me again and again, but chemistry for high school kids, and my education stopped there, is a science of breaking and forming chemical bonds. Means abrupt change of interatomic distances. Therefore, we need a tool that predicts formation or breaking of this, which is interatomic distances. And we need a tool that predicts forces and predicts the either attraction or repulsion of molecules enough to form or break these bonds. This interlaced in inserted cycles give this opportunity. And since the electronic structure tool that we use as this inside box doesn't include any information about presence or absence of bonds. It includes only information about positions and hybridization of orbitals, forming of the orbitals. So there are no constraints. The procedure will work equally efficient for reactants, products, or intermediates, and pathway between them. So it is a very powerful tool, and actually why we jumped from Gaussian to WASP, because this software and one of its sub-names is ab initio molecular dynamics code, because it is designed to predict how things are changing in time, how bonds are broken, formed. One of the first examples where they checked compared to experiment even before publishing all details how code is working, was melting and solidifying, annealing of liquid germanium, which is kind of a challenge, right? You need to go to high temperature, melt semiconductor, and for reaction surface chemistry works as well. It's good to not only for education but also for competitive research. Yes. Thank you much. I will try to be on the screen on Tuesday. I will, if you want request, I will send some additional information for your presentations, but I will look forward to see your slides on Wednesday night, in whatever 6 days from now. I will be very happy to consult, to give, answer any question or any materials, but we do not have formal meetings anymore before your presentations. Well, I will be giving an online lecture, but you can ask questions, but it is a little different than being really face-to-face.
So you're going to be back on Thursday then?
I will be back on Wednesday night.
Okay.
So I will, if I not see all slides, I will try to calm myself, and then if I will save time boiling up and sending friendly reminders and then non-friendly reminders. Thank you. Done.